were considering about decidability and undecidability. So, we were considering problems and instances of problem and what is a language representation. For example, consider a Boolean expression. Is it satisfiable or not? That is a decidable problem. Is it satisfiable or not? Given an expression something like that, x1 plus x2, x1 bar plus x2 bar plus something like that. This is a Boolean expression. Is it satisfiable means is there an assignment to the variables which will make the expression equal to 1. This is a decidable problem. You can definitely find out whether it is satisfiable or not, but there are several instances of the problem. Okay. What is an instant? An instant is an expression. One expression is an instance. Okay. So, you can have a Turing as a language you can represent this in some manner. For example, each variable you can represent as 1 0 power n means xn or something like that, some representation, or you can have say if there are n variables you can use log n bits to represent one variable and so on. So, one variable you can use using say some k bits, and then plus you can use, brackets you can use, like that you can use the symbols 0 1 for representing this plus symbol, then parenthesis and so on. With these symbols you can write a string, and you can have a Turing machine which will accept those strings which evaluate to 1 and which will not accept those strings which evaluate to 0. Like that you can have a Turing machine. So, this is a decidable problem, but as a language accepted. See, the problem is given an expression, is it satisfiable? As a language representation, how do you represent it? As this expression is represented as a string, and you can have a Turing machine which will accept those strings which evaluate to 1 and which will reject those strings which will not evaluate to 1. Now, the ambiguity problem again we considered, ambiguity problem, that is grammar is the input and is it ambiguous or not. Now, the instance of the problem is one grammar, and this one grammar you can represent as a string, okay, using some encoding for Turing machine. Like that grammar can be represented as a string. If it is decidable, then there will be a Turing machine which will accept all those strings, right, where the grammar is ambiguous, and they reject all those strings which are not ambiguous. Okay. So, there will be the corresponding language I can call as LLAMP, right. This consists of strings which represent grammars which are ambiguous. Okay. Now, when do you say that ambiguous is decidable? When do you say it is decidable? When this language is recursive. It has to halt and say, when do you say that a language is recursive? It corresponds to a Turing machine which halts on all inputs, right. So, it has to ultimately halt and say yes or no. So, here any string has to, the machine has to halt and accept or reject, okay, then it is decidable. If it accepts and stops, but when it rejects it gets into loop, means that is not decidable. Okay. The language has to be recursive. You have a problem and a corresponding language representation. The problem is decidable if the corresponding language is recursive, okay, not otherwise. Now, there are two cases if when it is undecidable. So, this is recursive, context sensitive will be here, and this is recursively enumerable. This is the hierarchy. So, if a problem is decidable, the corresponding language has to fall within this. Now, if it does not fall within this, it is undecidable problem. If it is undecidable, it may be here or it may be here. For example, this LU, we have seen some examples here. LU is here, LD is here, is not it? We have seen what is LD, diagonal language. What is LD? LD consists of strings Wi. Wi is not accepted by the ith Turing machine. We know that the Turing machine can be encoded using 0 and 1 and they can be enumerated. LD bar is the complement of that is Wi. Wi is accepted by Ti and Lu is MW, M accepts W, right, universal language. Now, Lu and LD bar are here. LD is here, Lu bar has to be here. The reason is, if a language is recursive, the complement will be recursive. Okay. If a language and its complement are both recursively enumerable, then it can be recursive. It has to be recursive. So, the thing is Lu is here, Lu bar will be here, LD is here, LD bar is here. The possibilities is for a language L and L bar is both of them can be within this, or both of them can be outside, or one here, one here. These are the three possibilities, and this we have already seen. So, problem is decidable only if the corresponding language falls within this. Even if it falls here or here, it is undecidable. So, the corresponding problem for LU is, does M accept W? This is the problem. The language representation is this. This problem, does M accept W, is undecidable. Halting problem is, does M halt on W? Slight difference is there. I mean, there is a difference. This is M accepts W. Now, we have seen two ways of proving the halting problem. Almost similar idea, but in one we showed that if the halting problem were decidable, then you will have a Turing machine for LD, right? That is not correct. Now, we have seen that LU is recursively enumerable, but it is not recursive, because we have seen that if LU is recursive, then we can have a Turing machine for LD bar. Now, there are several problems which are sometimes, okay, sometimes the word partially decidable is used if the language falls here. Language is recursively enumerable, but not recursive, then the word partially decidable is used. It is not a very common thing, or in books on logic that word is rather used. For example, the validity problem of propositional logic. What is the validity problem for propositional logic? The validity problem of propositional logic is similar to the SAT problem. In the validity problem, we try to find out whether a formula in propositional logic is a tautology, that is whether it evaluates to 1 always. In SAT problem, we try to find out whether there exists an assignment to the variables which will make the Boolean expression evaluate to 1. It is somewhat you can see the correspondence between that and the satisfiability of the Boolean expression. You have learnt about tautologies, contingencies and contradictions. When is it a tautology? You have to draw the truth table, and for last column you have to look into that. If it is all 1, it is a tautology, some 0, some 1, it is contingencies, all zeros, it is a contradiction. You can always find that, draw the table and find out, is not it? So, it is a decidable problem. What is the validity problem for first order logic? Given an expression, is it valid in the first order logic, is it valid or not? Like for all x, for all y, p of x y or something like that is equivalent to saying for all x, for all y is equivalent to saying for all y, for all x, okay, because if both are universal quantifiers, you can interchange them. If both are existential, you can change them, but if one is universal, one is existential, you cannot interchange. So, some expressions like that you can say that they are valid expression. Is there a way of finding out whether a first order logic expression is valid or not? Lot of work has been gone in that direction. Okay. So, for first order logic the language will be here, for second order logic it will be here. What is second order logic? Even the propositional things could be quantified. So, in first order logic individual variables can be quantified using, they can be bound using quantifiers. In second order logic even predicate variables can be bound using quantifier for all p where is p represents a predicate and so on. So, there are results like that, but we will not go into them. Some certain things like say given m is an encoding of the Turing machine, LE is m, L of m is equal to 5. Does the language generate the empty set? L non-empty is L of m not equal to 5. LR, all Turing machines, encoding of Turing machines, L of m is recursive, LNR m, encoding of Turing machines, L of m is not recursive. Some languages, the corresponding problem is given a Turing machine is the language generated empty. Given a Turing machine is the language generated non-empty. These are the problems. Given a Turing machine M is LM recursive. Given a Turing machine M is LM non-recursive. Input is the encoding of the Turing machine. These are all some problems. Instances of the problem will be particular Turing machine. Okay. And you are given the encoding, you have to find out whether it will it accepts the empty language, or is the language accepted non-empty, is the language accepted recursive, is the language accepted non-recursive, and so on. The corresponding language representation is this, right. For the language representation, the encoding of the Turing machine is the string which has to be accepted or not accepted, right. Now, this LNE falls here, it is RE but not recursive, right, but these things are not even RE. They are all undecidable, they are all undecidable problems, okay, because when do you say it is decidable? When the language is recursive. But here the languages are not recursive, but this alone is recursively enumerable but not recursive, it falls here, the other 3 fall here. So, the proofs for them, each one you can give a proof. The argument will be almost similar to what you consider for LD, LD bar, etc. There will be slight variations, but the arguments will be somewhat similar. So, I am not going into the details of that. In fact, there is a general result like this, Rice's theorem for recursive sets. There is another theorem for recursively enumerable index sets that we may not be able to consider, but this one we will consider. What is Rice's theorem? Let S be a set of recursively enumerable languages, each a subset of 0 1 star with 0 plus 1 star. That is, without loss of generality, we assume that the alphabet consists of only 0 1 and blank, of course. Input alphabet is 0 1, apart from that you have the blank. Actually, for any Turing machine you can just have only 1 and blank, 0 representing the blank and 1 symbol, that is also possible, but a number of moves to simulate any Turing machine with such a alphabet, that is 0 1, where 0 represents the blank, will be enormous. The number of moves required is enormous, and that is why we are not considering it. For our proofs, it is enough if we consider that the tape alphabet to consist of 2 symbols 0 and 1 and a blank. Blank is separate, 0 1, because any symbol you can encode in binary, that is the idea, right, that we have already seen. So, without loss of generality, we assume that the input alphabet is 0 1 and tape alphabet has 0 1 and blank, and S be a set of recursively enumerable languages. So, the whole family of recursively enumerable languages is this, means you are considering a subset S of recursively enumerable languages. Now, a language L has the property S. If L is here, L has property S. You say L has property S. A set L has property S if L belongs to S. S is a trivial property if S is empty or S is equal to the whole family of recursively enumerable languages. S is a subset of RA, right. Now, if S is equal to the whole set or if S is empty, it is a trivial property. Otherwise, it is a non-trivial property. Is S regular? Is S finite? I am sorry, L you have to say. Is L regular? Is L finite? Is L recursive? Is L empty? All these are non-trivial properties. They are all non-trivial properties. Rice's theorem states that any non-trivial property S of recursively enumerable languages is undecidable. Whatever property you take, if it is non-trivial, it is undecidable. So, L of S, the language representation for S, is the encoding of Turing machine such that L of M is in S. See, RE languages are this, L is S is a subset of that, this is S, right. Now, L is in S means L has property S. L will be accepted by a Turing machine M. L is a recursively enumerable set, so it has to be accepted by a Turing machine M. So, L is equal to L of M, right. So, if L of m is in S, the encoding of m, take the encoding of m, that is m, right. LS is a language which represents LS is a language which represents the encoding of Turing machine. L of m is in. Now, Rice's theorem says that L of S is not recursive, isn't it? Rice's theorem says that L of S is not recursive. There is another theorem which says under what conditions it will be recursively enumerable. It is not recursive means, so I told you it could be recursively enumerable but not recursive, or it may be here also. So, L of S, if S is a non-trivial property, L of S will be here or here. In which case it will be here, in which case it will be here, that is again in another theorem for Rice's theorem for recursively enumerable index sets, we shall consider later. What we want to prove today that LS is not recursive. Okay. How do you prove this? So, you prove like this: if LS is recursive, LU will be recursive, but you know that LU is not recursive. So, but LU is not recursive, therefore, LS is not recursive. This will be the argument. Without loss of generality, empty set does not belong to S. Assume empty set does not belong to S. Otherwise, you have to take S bar complement of that, does not matter. So, S is a non-trivial property therefore, there is some L belonging to S, there is some language belonging to L, and L is accepted by a Turing machine ML. The corresponding Turing machine is ML. L belongs to S, there is a language L belonging to S, and L is accepted by a machine, Turing machine, call it as ML. Now, you construct a machine, machine means Turing machine, M dash as follows. How do you construct M dash? The structure of M dash will be like this. what m dash will do is it will simulate the behavior of m on w, it will ignore the input x. For m dash the input is x, it will ignore that, but it will simulate the behavior of m on w, and if the answer is yes, it will start ML, and then for every MW you can construct a machine m dash as follows. For every pair of m and w you can construct a machine m dash like this. What m dash will do is it will ignore its input, right, but it will simulate the behavior of m on w, and if it is yes, then it will start ML. If it is no, ML will not be started. If ML will be started and it will work on x, and if x is accepted by ML it will say yes, if it not accepted it may get into loop or reject. If it is yes it will say yes, otherwise. So, what is the language accepted by m dash? What is the language accepted by m dash? L of m dash, if m accepts w then this will be started, and if this is started it will accept L. ML will accept only the language L, isn't it? ML is the Turing machine for L. So, L of m dash is L if m accepts w. For every pair m w you can construct a machine m dash like this, right. It will m dash ignores its input initially, it simulates m on w, and if the answer is yes, okay, ML is started and it works on x, and if the answer is yes it will say yes. So, if m accepts w only this will be started, and it will accept just the language L. Whichever string is in L it will accept, whichever string is not in L it will not accept. So, L of m dash will be L if m accepts w. L of m dash is equal to empty. If m does not accept w this will never get started. So, the language accepted will be empty. L of m dash is empty if m does not accept w. Right. Now, S is a non-trivial property. If this is the family of RE languages, S is here, and we have seen that phi is not in, it is not in, phi is here, L is here. Okay. Now, suppose S is a decidable property, then what can you say about LS? It has to be recursive. LS is recursive if S is decidable. So, there will be a Turing machine MS for that, right. Now, this is the Turing machine MS. For this give the encoding of m dash. If it says yes, what does that mean? If it says yes means Lm dash is L, right. When is Lm dash L? If M accepts W. So, M accepts W. If it says no, then M does not accept W. So, you are able to say whether M accepts W or M does not accept W. That is LU is recursive, but LU is not recursive. I will write this diagram in a slightly different manner. Okay. So, given MW, right, you have an algorithm which will construct M dash, this construct M dash, and the encoding of M dash is given as an input to MS. Right, and if this says yes, that means M accepts W. If this says, see, we are assuming that this is a recursive and though there is a Turing machine which halts on all inputs. L of S is recursive if S is a decidable property. So, there is a Turing machine MS which halts on all inputs. So, it will say yes or no, M does not accept W. That means you are having a algorithm for LU, or you are having a saying that the problem whether does M accept W is decidable. This is an algorithm for LU or a Turing machine which halts on on all inputs, right, which is a contradiction. We know that LU is not recursive. If you assume that this property, non-trivial property, is decidable, then you come to the conclusion that LU is recursive. So, the argument is like this: if LS is recursive, then LU is recursive. That is what we have come to the conclusion. But we know that LU is not recursive, that is a contradiction. So, LS is not recursive or S is not decidable. This is for any non-trivial property. So, any non-trivial property of recursively enumerable language is undecidable. So, this sort of an argument, initially it may look a little bit not very convincing or somewhat confusing. If you read the argument again and again, it will become clear. I am doing only this theorem, Rice's theorem only. If you look into the proof from the book, L empty, L non-empty, L recursive, all the proofs will be similar, there will be slight difference in each one of them. That is why I said you have to be very clear as to what you want to prove and so on. Okay. So, under what condition? We know that LS is not recursive, but under what condition it is recursively enumerable, that is another theorem. Under what condition it is not even recursively enumerable, that is you can find it. So, as I mentioned earlier, is L empty, is L recursive, is L non-recursive, they are all the corresponding languages fall here. Is L non-empty false here. Similarly, is L finite, is L infinite, is L regular, does L have at least 10 elements, does a particular member belong to L, all those things are non-trivial properties. Trivial property is when S becomes the whole set or the empty set. Is L recursively enumerable? That is a trivial property because it is S for all recursively enumerable languages. So, whenever you find that there is a non-trivial property of recursively enumerable language, you need not even think about this detailed proof, immediately use Rice's theorem and say that it is undecidable. Okay. So, does W belong to L, or given a type 0 grammar, will it generate a string W? That is an undecidable problem. So, that is called the membership problem. Membership problem or for a Turing machine corresponding to does M accept W. As a grammar, type 0 grammar if you take, does G generate W? If G is type 0, this is undecidable. As a Turing machine, we know that this is undecidable. Whereas the membership problem for context sensitive languages is decidable. Context free languages it is decidable, for finite state automata or type 3 languages it is decidable. In the question of how much time it will take to find out whether W can be generated by a grammar, if it is right linear, if it is context free and so on. So, if you look into the membership problem, for FSA, does FSA accept a string W? How much time it will take? Function as a function of the length of the input. W is W accepted by a finite state automaton. The length of W is equal to N. Is W accepted by M, where M is a FSA. How much time it will take? You have to just look into that. So, N order N time. Membership problem for FSA you can solve in linear time. For CFG or CFL, it is does G generate W? This is the membership problem for context free languages. There are algorithms like CYK algorithm, Kake Younger Kasami algorithm and Early's algorithm which solve this problem in order n cube time. Some manipulation you can reduce it to slightly less than 3, like matrix multiplication you can reduce using Strassen's matrix multiplication, like that some L 2 point something you can reduce, but that is a very difficult proof. Generally you can do it in order n cube time. In fact, sometimes if the grammar is unambiguous, it will work in order n squared time. Early's algorithm will work in order n squared time if the grammar is unambiguous. But finding out whether a grammar is ambiguous or unambiguous is undecidable problem. Now, for context sensitive language, membership problem is said to be piece-space complete. we will see that later. Another thing is for type 3 grammars the automaton is FSA, and in FSA deterministic and non-deterministic version are equivalent. Type 2 grammars CFG, the automaton is push down automaton. Type 0, it is Turing machine. Here the non-deterministic and the deterministic version are not equivalent. Here the non-deterministic version is equivalent to deterministic version as far as accepting power is concerned, but the number of steps will be exponentially increased when you try to simulate a non-deterministic machine, Turing machine with a deterministic Turing machine. What is the automaton for type 1 grammars? It is called LBA or linear bounded automaton. Linear bounded automata. What is a linear bounded automata? It has a tape which is linearly bounded with n markers. You have a tape, the input will be given on the tape, the machine will start here in the initial state. The behavior is just like a Turing machine. Any time it can read a symbol in a state, mapping will be just like this, delta of QA is equal to P A R R L. So, it will change its state to P, print A, move right or move left. Mapping is exactly similar to Turing machine, but it cannot, it has to move within this. If it tries to reach this cell or reach cell, the input will be, the machine stops. If it reaches the end markers, the machine halts. So, it has to move within this space only, whereas a Turing machine is infinite in both directions or one direction, whatever it is, one way infinite. Here the tape is finite and behavior mapping is similar to that of a Turing machine, but if it reaches this cell or this cell, machine halts. Within the end marker it has to move. It is linearly bounded, the tape is linearly bounded, that is why it is called a linear bounded automata. Here again it has been shown that type 1 grammars are equivalent to non-deterministic linear bounded automata. You can give a proof saying that given a non-deterministic linear bounded automata, you can have a context sensitive grammar, given a context sensitive grammar, you can have a non-deterministic linear bounded automata. But if you take any context sensitive language, you are able to construct a deterministic linear bounded automata. Whereas in the case of push down automata for WWR or certain languages, you are not able to construct a deterministic push down automata. Here whenever you take a context sensitive language, you are able to construct a deterministic linear bounded automata. Proof showing the equivalence uses non-deterministic linear bounded automata. But so far any context sensitive language if you take, you are able to construct a linear deterministic linear bounded automata for that. So, whether non-deterministic LBA is equal to deterministic LBA is an open problem. Till now it is an open problem. Now, Rice's theorem says that any non-trivial property of the recursively enumerable language is undesirable. So, any property if you take, you can very easily say it is undesirable or not. But what about properties of Turing machines? Properties of Turing machines. Properties of the languages accepted by Turing machine is the properties of recursively enumerable languages, that very easily we can say whether it is desirable or undesirable. We need not have to go through the entire proof. Once we know that it is a non-trivial property, immediately we can say it is undesirable. But what about the properties of Turing machine? What do you mean by a property of a Turing machine? Certain properties, like does the Turing machine have 5 states, okay, or the simple things, it is decidable. There are other properties which are undecidable. For example, given a Turing machine, start it on a blank tape, will it ever print 3 ones, consecutive ones? Without loss of generality, assume that the alphabet is this, then start on a blank tape, will it ever print 3 ones? That is an undecidable problem, right. So, properties about Turing machine, some of them are decidable, some of them are undecidable, and there is no systematic way of approaching is that. Each problem you have to look into the problem and find out whether it is undecidable or not. So, the question is, does a Turing machine started on a blank tape ever print three, or not even on a, that's it. Three successive ones. This is undecidable. How do you prove that this is undecidable? Given M, construct M cap which simulates M on blank tape. Now, for M the symbols are 0, 1. For M cap, 0 is represented as 0, 1, 1 is represented as 1, 0. So, suppose in M I have at some stage I have the tape 0, 1, 0, 0. M cap I will have the tape 0 is represented as 0, 1, 1 is represented as 1, 0, 0, 1, 0, 1. So, whatever tape is here in M, non-blank portion of the tape is there for M. M cap, if you represent, it will not have 3 consecutive ones, because 0 is represented as 0, 1, 1 is represented as 1, 0. Okay. And also when you make 0 into 1, 0, 1 has to be made into 1, 0, right, and you do it in such a way that first you change the 1 to 0 and then the 0 to 1. 1 by 1 only you have to change. If you change 0 to 1 first, at one stage you will have 2 ones, no, that you avoid. If you want to change 0, 1 to 1, 0, first change the 1 to 0 and then the 0 to 1. Similarly, when you want to change the 1 to 0, 1, 0 has to be changed to 0, 1. So, first change the 1 to 0, then the 0 to 1. This way you make sure that always 0 you change the 1 to 0 first avoiding at any stage appearing 3 once appearing. Okay. So, m bar is just m where every 0 is represented as 0 1 and 1 is represented as 1 0, and because of the way we have chosen the representation for 0 and 1, it will not have 3 consecutive ones. If m accepts and halts, m bar will print 3 ones. If m accepts, m cap will print 3 ones. So, if the problem whether a machine will print 3 consecutive ones or not is decidable, you can start m on blank tape and see whether it will accept or not. What is that problem? The problem is, does m halt in an accepting state started on blank tape, and this is equivalent to the problem does epsilon belong to L of m. Does epsilon belong to L of m or Lm contains epsilon? That is a non-trivial property, is not it? Right? It is a non-trivial property. Does epsilon belong to L of m is a non-trivial property. By Rice's theorem, that is undecidable. Now, if you assume that the problem whether the Turing machine will print 3 ones at any time is decidable, then you come to the conclusion that does epsilon belong to L of m is decidable, but that is an undecidable problem. So, does a Turing machine ever print 3 1? This is undecidable. Now, this is a property of the Turing machine. It is not a property of the recursively enumerable language, it is a property of the Turing machine. Similarly, there are several problems about Turing machine. There is no systematic way of tackling that. Rice's theorem helps us to tackle the problem decidability or undecidability of problems on recursively enumerable languages. But about Turing machines, each problem you have to look at it and find out a solution, right. So, this is something about decidable and undecidable problems of Turing machines and recursively enumerable languages. Next, we have to consider some more problems like post correspondence problem, and using that how some decidable problems like the ambiguity problem can be solved. So, we shall consider in the next class.